Liksom.
This is why you need a production team.
Yes.
You need to do this before.
Hör du någonting?
Där var jag live.
Nu är chatten igång här med.
Gött.
Alltså vi beslutar någonstans mitt i.
Okej.
Nej, men jag är tillbaks nu. Så här ser det ut nu.
Mm.
Det här är tidigare. Ser du det inte? Det är det gamla som streamas, som är inspelat. När börjar det nya? Det är för 33 minuter sedan.
Ska se om det är samma länk bara.
Det här är det gamla. Mm.
Ja, nej, det är inte samma.
Då kan man gå in och göra ett inlägg i den gamla länken och säga byt länk.
Nej, jag tror inte man kan det nämligen.
Man kan göra en kommentar.
Nu kom Stavros in här ju.
Okej.
There is sound. Kan det vara att...
There is sound, there is light. Det är bra.
Nu är inte nervös.
Jag förstår.
Kan du chatta in där och säga vad hör ni? Vad hör ni?
Jag se hur det... 4 tittar. 4 har ju ändå hittat den här nya länken. Så att det måste vara att de är i samma kanalen då.
Då ska jag kunna... Jag kommer hela tiden inte det gamla. Hur ska jag kunna...
Går det inte att spela fram? Jag menar, du verkar ju kunna titta på vilken del du hittar.
Ja, så salivet. 12:36.
Ja, nu är jag framme. Nu är jag tillbaka i länken. Nu håller vi på att peta här. Ja, nu kommer det någon tjej in plötsligt. En
Det är som
dam.
att man har administratörsrättighet på något sätt. Det är man tror att man
Nej, alltså jag är ju inne på hennes liksom... Jag förstår inte, några har ju hittat hit redan. Så att,
Ny är ny. Ja, det är fortfarande gamla som kommer upp när jag äter. Här är ditt test igår. Då skickar vi ut den där. Jag kan ju skicka ut till alla i huset i och för sig. Det kan vi göra.
Det kan du göra.
Har du den länken då? Kan du mejla den till mig på något sätt? Har du massa e-mail här nu när jag får det, så nu kan vi lägga till det, Eva?
Det är inte e-mail, det är Facebook, det är LinkedIn, det är vissa e-mail.
Då du får den här då, du får en länk till just.
Ja.
Så de join allt eftersom du kan lägga den på dem.
Så.
Okej.
Det här är lite märkligt för det är inte tekniken här som har lagt av. Det är...
Susanna lägger ut det här på hemsidan också.
Ja.
Alltså det är 9 så
Vad sa du?
Det som gjordes bara upphörde utan någon uppenbar anledning.
Det här ser ut att vara live.
Har han skickat länken?
Nej, jag fick ju en sån här du streamar live för att det är mitt konto. Men jag vet inte om jag ska få in. Det är en sån här jättelång. Nej, jag vill bara.
Nu har jag ljud, jag skickar ut länken. Har ni fått ett e-mail? Vi gick till huset.
Vi moderator på den.
Ja, Mikael Bergman har svarat. Soundworks. Emanuel Haglund. Checka ut länken igen till samma mejllista som innan. Fråga. Nej. Ska skriva ett men de vet inte. Men han ser ju den. De kan vara inne i chatten. Kan de skriva det?
Chatten? Ja.
Hur har du skickat den till Emanuel?
Har det gått ut till huset?
Ja.
Men
Prefektens mejl är Jack. Nu ska vi titta.
Ett spanskigt projekt.
Ja.
Laddat på till du lägger. Ja, Mats lägger. Vilken länk är det på?
Jag har inte heller fått den där.
har du inte?
Nej.
Jag skickar den till.
Den fick skicka till sätt. MC2. Ny länk. Den modereras den där listan. Va?
Ja.
Vem är det som modererar den?
Tror Susanna.
Nu kommer.
Okej.
Ja. Men då kan vi ju köra igen för då hoppar ju folk in här nu.
Okej. Bra. Har ni fått den där?
Jag måste skicka till.
Mikael, jag har fått den.
Jag har inte fått den. Jo, nu kom det.
Nu kommer den.
Okej, men då kommer det här till allihopa alldeles strax.
Okej.
Då kan vi ju kicka igång igen.
Yes.
Kör vi.
Det är Susanna lägger ut info på Kjellens hemsida också.
Ja.
Så vad är det som streamas just nu? Är det Svarta tavlan?
Alltihopa.
Okej, så då tar jag suddar ut här då.
Jag slår på projekten igen.
Ja. Provar vi igen. All right, sorry for this. We will come back with the presentation by Nicky here in a second. So we lost the sound after 12 minutes and 36 seconds. So hopefully you will be back again. Please distribute the link that was sent out to you, to your friends and to colleagues, so everybody is up to date where we are on YouTube. So welcome back. And Nicky, are you there?
Yes, I'm here.
Good. Okej, Eva. Eva, kan du dra ut sen?
Vad liten du är. Nej, han sa share screen.
Stora. Okej. Go ahead.
Okay, so can we continue?
Yes.
Yes.
Okay, thank you. Thank you very much. So we have this mature technology based on gallium arsenide VCSEL arrays supporting interconnect infrastructure in data centers today and in supercomputers and so on. But so what's the need to improve then? And what we have seen over the past few years is that the data centers are getting larger. So whereas in the earlier days, one would have a couple of racks in a room, or maybe several floors in a building. Now a data center will become the size of a football field or even larger. And in the upper right corner, you have a picture from a data center that Google is building in Belgium, for instance. It's a huge size, and of course that requires in interconnects covering these distances in the range of from 1 to 2 kilometers. So if we look a little bit kind of qualitative picture, I try to show here the green bars at the lower side of the slide are showing a kind of reach that various types of interconnects cover in the data center. So we have the board-to-board or within a rack. It's up to 10 meters, and then between different racks, rack to rack, it's from 10 to maybe 100 meter maximum. And then from 100 meter, we will need to bridge to 1 kilometer and 2 kilometers based on the evolution of the data center today. And of course, we have this technology based on VCSEL arrays and multimode fiber, essentially gallium arsenide emitting around 850 nanometer, which is very well suited for the short reach, the very short reach up to about 100 meter. Of course, it says here 100 to 300 meter, but that is, of course, dependent on the data rate per channel. When we are at 28 to 56 gigabit per second, that reach is rather limited to about 100 meter today. They support massively parallel links. So many channels that do not need maxing or demaxing. That is important to reduce power consumption and as well to reduce latency. And one usually refers to this very short reach links as no latency or very, very short latency links. And then at the other extreme, we have the edge-emitting laser-based communication links with single-mode fibers, typically 1300 nanometer emitters. They can support some channel count, 4 to 16 channels per module, today maybe 1 to 2 fibers with 4 to 8 wavelengths per fiber, coarse WDM, and probably up to 112 gigabit per second per channel today. What is very good with the edge emitting technology of 1300 is that can easily go 1 to 10 kilometers. And there is some latency, but it's moderate. This is primarily due to the maxing and demaxing and clock data recovery that needs to be done for, especially going 2 kilometers and longer. But as we see on the blue line above, the edge emitters are good down to some kilometer, but then below 1 kilometer, the issue is that they do not scale well for the large channel count and low latency that we need on the shorter links. At the same time, the multi-mode fibers cannot reach beyond the 100 meter, especially at the higher data rates. And we would expect that even 100 meter would be difficult if we try to increase the data rate per channel beyond 56 gigabit per second. So we have some kind of gap between 100 meter and 1 kilometer. And in my opinion, one of how should I say, the preferred solution should be to try to extend the reach of the VCSEL array-based technology, and that is because that will bring all the benefits of the massive parallelity that this technology and low cost and low power consumption per bit or per data rate. Right? So here comes Eva's contribution that she will present today. I think this is a very important topic today for pushing forward the communication capability in the data center, improving performance, making possible to increase the interconnection density also between 100 meter and 1 kilometer. I think this is critical for the continued development in the direction we have seen the last few years. Yes, thank you.
Thank you, Nicky. So then it's time for Eva to present her thesis work. So welcome up to the stage.
Thank you. All right. Hello, everyone. In order to use the features of being able to point with the laser mouse, I will be sitting down. I hope that's not too boring for you. All right. All right, so my work is titled Longer Wavelength Gallium Arsenide-based VCSELs for Extended Reach Optical Interconnects, where the VCSEL is a type of laser, and I will jump right into why the Extended Reach Optical Interconnect is needed. So most of you are familiar with large service providers such as Facebook and Google.
Sorry, Eva, could you share your screen so we see the view graphs?
It's not shared, okay. Sorry, of course. Of course. It's here. I think. Screen 2. Share. Isn't this good?
Yeah, now it's good. Thank you.
So, yes, sorry. And I will use pointer option laser. So, as I was saying, most of you are familiar with the Google and Facebook, which are very large service providers. And to you, it will come as no surprise to hear that most of the data center traffic to end user is with video streaming. However, businesses take up most of the traffic inside the data centers, and the cloud edge computing advances in co-location as well as hosting is increasing this demand. So the better part of the traffic of a data center takes place within the data center. And here, big data, I think we can see it if I point. I don't think you should do that. Thank you, Peter. Oh, sorry. Too much. Do we need the top of the slide, maybe? So, okay. All right. So, yes, inside the data center, big data is the biggest increasing application. And data centers are exploding in size in order to accommodate for this traffic demand. And the major incentive for this is sustainability. That's why hyperscale data centers that are enormous in size differ from traditional DCs by they make use of the advanced infrastructure, and they use state-of-the-art power, cooling, telecommunications, artificial intelligence, operations, and software and hardware in order to make truly energy-efficient data traffic. And by this year, hyperscale data centers will house less than half of all data center servers, but the hyperscale data centers will be processing, will be doing 68% of the processing, and it will store more than 57% or 57% of the data that is stored in the world. And if we then take a look at the energy demand by data center type, hyperscale data centers only take up 40% of the energy. So it's all about sharing resources under the same roof. This is the largest data center in the world. It's owned by Range International Information Group and it's situated in Langfang, China. It's almost 600,000 square meters large. Another company that caught my eye was Switch. They have marketed themselves as being a sustainable service provider, and they put effort into the entire infrastructure of the data center in order to provide energy efficient solutions. And they have a Citadel campus that has several data centers, but together they consist of more than 1.6 million square meters. And I encourage you all to take a look at their video gallery at switch.com. Especially, I wanted to show this movie, but due to these circumstances, I would like you to yourself go into this website and take a look at the Core Campus video. And they have a section in it that shows over 1 mile of server corridors, which is pretty cool. So it is easy to then understand why up to 2 kilometers of optical interconnects are needed. So this is the outline for the rest of the talk. So far, we have gone through why this healthy development towards hyperscale data centers raised the need for these energy efficient, high-speed, and long-reach optical interconnects. A long-reach optical interconnect could open up possibilities to use new and better ways of connecting servers in these data centers. And a typical architecture is shown in this image here. If you use a powerful architecture to connect the servers and components that go with it, you can substantially improve the energy efficiency, the capacity, and also the speed of data center traffic. So we will wonder then what is a good approach, and there are many options to choose from, and we will take a look at those options, but also motivate why we chose the gallium arsenide VCSEL, and then especially why we chose to focus on 1060 nanometer gallium arsenide VCSELs before we go into the choice of fiber and a little bit about the design. So that's what's coming up. So the vertical cavity surface emitting laser, the VCSEL, has a circular output beam, and compared to a edge emitting laser, for instance, this one, the vertical surface emitting laser, emits light vertically to the active region, which is indicated in red here. And the circular output beam fits great with the circular core of a fiber. And the detector in the other end of an optical interconnect detects the light. So the way the VCSEL is structured makes it good for 2D array fabrication. You can do on-wafer testing. If you've seen the front page of my thesis, you see an array of VCSELs. You can fabricate them next to each other, and it allows for flexibility in design as well. And the small active region of a VCSEL will also allow for a low threshold and driving current, as well as low power consumption. And direct modulation can be made very high speed. This is often packaged as an active optical cable, the VCSEL, the fiber, and the detector, along with some other components. And this is a standardized solution at the wavelength of 850 nanometers. Then you use a multi-mode VCSEL and a multi-mode fiber. These standardized multi-mode optical interconnects have a limited reach. They usually are limited to about 100 meters at the speed of 25 gigabits per second. If you lower the speed, you can go further. But at that bit rate, it's about 100 meters, and it's mainly due to chromatic dispersion and attenuation in the fiber. So, other technologies that could be used, except for this top one, short wavelength 850 nanometer using multimode VCSEL, multimode fiber, are a longer wavelength, so 1310 and 1550 nanometer single mode VCSELs, edge emitting lasers, electroabsorption modulated lasers, and single mode fiber. You can also use silicon photonics, which is as well available in coherent technology as coherent technology. But the gallium arsenide VCSEL-based optical interconnects are, as we saw in the previous slide, superior. They provide a superior cost and power efficient solution because of the VCSEL is superior to the edge emitting laser, for instance, because of this. And then we have the VCSEL also has a small footprint. They can make a small footprint transceiver, and because of the gallium arsenide, we will encounter a lot of benefits as well, which I will discuss on the next slide. But how do we extend the reach? So these multi-mode optical interconnects were limited in reach. So how do we extend the reach with the gallium arsenide VCSEL-based technology? Well, our solution that we focused on was 1060 nanometer VCSEL. So with the gallium arsenide technology, we strained the quantum wells with indium in order to get to 1060 nanometers. And if we look at what happens in the fiber, we will have an improvement in the loss. So we will have half of the attenuation in the fiber, and we will have less than 2/3 of the chromatic dispersion when we move to the wavelength of 1060 compared to 850. And then when we look at the VCSEL improvements at this wavelength, the strain will move us from gallium arsenide with a bit of indium in the quantum wells. We will get to 1060, which means we will have strained InGaAs quantum wells, which will improve the speed of the VCSEL. And the quantum wells will be deeper, which can lower leakage currents. And the band gap will be smaller to lower drive voltages. You can also, since gallium arsenide becomes transparent at 1060, you can also use binary materials such as gallium arsenide, aluminium arsenide in the bottom of the device in order to get lower thermal impedance. Okay, so sorry for quickly jumping to the next slide, but this is about single mode and multimode VCSELs and single mode and multimode fiber. So just to explain the benefit here of using single mode VCSEL is that the standard optical interconnect using multimode VCSEL and multimode fiber has a VCSEL that emits in many modes. So except for this mode, the fundamental mode that usually has a very straight path through the fiber, you can also excite higher order modes in the fiber with the many modes of the VCSEL. This combination has a relaxed alignment tolerance, and but however, the reach of them was limited by modal and chromatic dispersion. And then if you instead use the same fiber, but you use a single mode VCSEL, with the help of selective modal launch, which is a special launch condition, you can reduce the effect of modal and chromatic dispersion in the fiber, which takes you further. But then if you use the single mode VCSEL together with a single mode fiber, which has a much smaller core, you will eliminate modal dispersion, and you will also reduce the effects of chromatic dispersion because you have only one fundamental mode propagating. So single mode VCSELs is of particular importance for longer reach optical interconnects, and that's why we, in my work, decided to focus a little bit more on single mode VCSELs. And how do we make a VCSEL single mode? Well, there are, here I present two ways to do it. So one way is to reduce the oxide aperture size, because the modes of a laser have a a certain distribution, a spatial distribution. So by introducing, you can introduce loss or just narrow the oxide aperture, so the active region, the area that is used for lasing, you will cut off the higher order modes, and eventually when the VCSEL is small enough, you will only have fundamental mode emission. And another way to get a more single mode design is to reduce current spreading to confine the optical gain. So we have two designs, design 1 and design 2, that we have developed and compared. And the difference between them is the distance between the oxide aperture, which confines carriers, is further from the active region in the first design than it is in the second design. It's a factor of 10 in distance between these designs. This makes, when you look at the spontaneous emission near fields, this makes current spreading around the active region, underneath the threshold. This was measured underneath the threshold. Current spreading is less in the more confined device, and that will give you an gain in a more confined area, which will give you more single mode emission. And also lower beam divergence. A benefit from a system point of view of single mode VCSELs is that they have single mode VCSELs have small spectral width, and also you don't have to worry about mode competition penalties. Okay, so also if we take a little bit a deeper dive into the VCSEL design and dynamics, we can see that a VCSEL behaves as it has a two-step. Oh God, the words escape me. We can describe the frequency behavior like this. So the dynamic behavior, if we increase at a certain frequency, the output of the VCSEL will the VCSEL will have a certain bandwidth, and we can see if the resonance frequency of the VCSEL is higher, the bandwidth will be larger, and the damping affects how much how peaked the response will be. And the active region plays a big part in this. We have our strained INGAS quantum wells, which provide a higher differential gain. And that goes into the D factor here, which affects the resonance frequency. And the short cavity gives us a very strong optical confinement. We have DBRs, which are mirrors on each side of the active region, and they have been designed for a very low resistance and optical loss product. And a very important part in my work has been the top DBR reflection. So we can adjust the reflection on the very top of the VCSEL in order to optimize the photon lifetime of the device, and therefore tune this damping of the device and get a nice broadband or high bandwidth response. So this comes into the equations over here. And then we have multiple oxide layers that reduces capacitance, and also very thick BCB around here to planarize the structure. And when we do that, we reduce pad capacitance. So both these reduce the parasitics of the device. And last but absolutely not least, the primary oxide layers. They are responsible to confined carriers, and we have a design. Our designs have very high internal quantum efficiency, and the oxides also are designed to be positioned in optical field nodes. So our designs are very weakly guided. All right, so now that we have taken a look at the VCSEL, the gallium arsenide VCSEL, we will quickly take a look at the challenges I've encountered in my work. So this is a little bit more fun. So I'm not going to go through all of the points here. I'm just going to highlight a few of the challenges I've had. And one is when you get the material, you have with including doping and graded interfaces, you have 400 layers that you need to validate and also perform oxidation tests. I do a lot of material simulations in order to perform etching in fabrication, and fabrication requires every feature of the VCSEL requires a pattern, and we design these patterns using CAD, and this is shipped during fabrication. So you see the many VCSELs on this chip, and the patterns are made by these masks. Fabrication, if you take a look at some of the points in fabrication, these are not all of them, but at some of these points you can see development that goes from putting out the mask, the pattern for the top contact, which is then deposited, and then following through, you have eventually finished device and at the end here. And the lacing part is the very center part, the circle in the center. Another challenge is the setup design. The mechanical build can sometimes be complicated. Here we use a piezoelectric positioner in order to align a fiber to the output of the VCSEL that goes through a lens system. And components for testing isn't trivial at 1060. Not much is standardized. So, for instance, Fibers has been in collaboration with Corning. They have provided us with fibers that are excellent at 1060 nanometers. Optimization is a big part. For instance, the VCSEL design needs to be optimized. Oxide apertures, mirror reflectivity, as I mentioned. Mesa sizes, we found that by reducing the size of the mesa size, we could reduce the capacitance quite significantly. And when we choose driving conditions, so you need to choose an optimum point for driving the VCSEL in order to get the response you want, because it affects the dynamics and the large signal transmission with overshooting, ringing, and so on. And then noise reduction. I've made many measurements where I've measured noise, and measuring noise in a noisy environment is very challenging. And last but not least, again, revising theory and doing calculations and simulations. That's a big part of the work. So we are coming into the last part of the presentation, which is results and then straight to impact. So in papers A and B, we focused on single mode and multi-mode VCSELs. You see single mode emission here and multi-mode on the bottom. And then we can see that the bandwidth that I've mentioned is sufficient and nice for both of these designs, better for the smaller VCSEL in this case, which is the single mode one. So for both the single mode and multi-mode VCSEL, we made transmission experiments. And for the single mode VCSEL, we achieved, we tested 25, 40, and 50 gigabits per second at 2 different temperatures. And in back-to-back, which means without any long length of fiber, so very short length, almost 0 meters, we achieved 50 gigabits per second at 25 degrees Celsius. But with a fiber, a 1 kilometer fiber, we made preliminary measurements where we achieved 25 gigabits per second over 1 kilometer of multimode fiber using this single mode launch. And then in paper C and E, we measured frequency chirp, which happens when you modulate the VCSEL and the VCSEL needs to undergo oscillations in order to stabilize at each voltage level. It will, in some turns, result in frequency chirp. And we saw that the chirp that happens, which is this peaking at the, if you look at the signal, zeros and ones, zeros, 1, 0, 0, 1s, you see that the frequency makes jumps. And we saw that this in combination with the negative fiber chromatic dispersion, it makes the pulse, the energy of the pulse will compress at a certain distance. So it compresses the pulse before it then again broadens. So there is an optimum distance for when we have a narrow pulse that can be transmitted this optimum distance. Let's see. So when we measured and gained our results for 40 gigabits per second over both 1 and 2 kilometers, we saw that when we went from back to back, which is the blue curve here at the higher rate, which was 40 gigabits, we saw a power penalty compared to when using the 1 kilometer long fiber. And then at 2 kilometers, we were back in the normal pattern where the pulse is broadening again. And then we also in paper E used pre-emphasis, is when you drive the VCSEL with a signal that isn't purely ones and zeros, but you have a pre-emphasis. And then we achieved 50 gigabits per second over 1 kilometer of SMF using this method. And then we also, in paper D, looked at noise performance. So we used single mode VCSELs again, but here we had tuned them. The top layer of the VCSEL, as I mentioned before, had been tuned for one with a very damped modulation bandwidth and one with a very resonant modulation response. And when we measured RIN for these two devices, we saw that the RIN with the damped, this is the damped VCSEL, was lower and actually came down to the noise floor very at higher bias currents, while for the peaking or resonant VCSEL, the relative intensity noise, the RIN, so its intensity noise of the VCSEL was much higher at these different frequencies. And we also measured the line width, so the relative intensity noise is a measure of intensity noise, while this amplitude noise, and this line width is a measure of the phase noise. So we measured the line width of the VCSEL, and we saw that the more resonant VCSEL had a much wider line width than the damped one, which is summarized here. So intensity and phase noise was strongly dependent on the resonator loss, but we actually saw almost no dependence on current confinement. It was very small. And the RIN went down to the shot noise level at higher currents for the damped VCSEL. And we also measured some of the smallest line width measured for single mode VCSELs. And in paper F, which is the last paper of my thesis, we investigated short reach OM5 transmission, starting with PAM4, which is pulse amplitude modulation. It basically means that we have two levels if we used PAM2. And this is represents a 0, and then you have a 1. So there we achieved 60 gigabits per second using equalization, which can be seen here. Both of these curves. One uses preemphasis. Both uses equalization, and one uses pulse shaping. And then PAM4, there's no difference in the spin in PAM2, but when we use 4 levels, the equalized signal achieved 100 gigabits per second over 100 meters of OM5 fiber, and the equalized plus the pulse shaping gave us 110 gigabits per second, which is makes it suitable for WDM, which is wavelength division multiplexing. So this opens up for the possibility to use not only 1060, which is the wavelength I use, but also between the standard wavelength of 850 and 1060, you could use 30 nanometer intervals and have 8 carriers with data in the same fiber, which will lead to a very high aggregated speed. And the impact of my work. So first of all, I've made 1060 nanometer VCSELs that have shown state-of-the-art performance in terms of speed, noise, and efficiency. So that's one achievement. And then also I've provided lots of characterization, such as line width, chirp, and many more pieces of information about both VCSELs in general, and but in my case then about 1060 nanometer VCSELs. And then you can use these VCSELs in order to make single lane extended reach optical OIs. So one of these 1060 nanometer VCSELs together with fiber can provide a cost and energy efficient solution. And also in these architectures in the data centers, you could avoid a congestion limit by replacing many fibers that are shorter with one of these longer ones. And third, the aggregated terabit per second links with longer reach, which is one of the goals of the Ethernet standard. They are aiming to do 1.6 terabit Ethernet by adding parallel lines, so many optical interconnects next to each other, and then also employing this higher order modulation. PAM4 is most commonly used, and then also you can use the wavelength division multiplexing in order to reach aggregated speeds. And I would like, as a final slide, to acknowledge my collaborators, Hewlett-Packard Enterprise and Corning, Eurojacek, and Politecnico di Torino in Italy have all been contributing with their knowledge, and yes, it's been a good collaboration, while SSF and VR have funded the work, and IQE provided us with epitaxial material. I would like to thank you all for listening in, and the chair will take over and let us know what happens next. Thank you.
So thank you very much, Eva. Great presentation.
I guess I could stand here.
At this moment, we would really like to have an opponent at the stage here, but can we get him up on the link, on the YouTube link or not? We cannot. So we will only hear the sound.
Yes.
Then I leave the word to the opponent, who will ask you some questions about the technical details and the science behind this.
Yes.
So please. Make your round. Yeah. Good.
So thank you very much for a very interesting presentation, Eva. I think maybe you can sit as you did for the presentation. It's maybe going to take a little bit of time, our discussion.
Yes, I guess they don't need to see the top of the slide. In that case, I'll make it work. So.
Yes, right. So again, thank you very much. It was a very interesting presentation. Now we argue that VCSELs are very good, very well suited for optical interconnects, at least for the short reach. But why an optical interconnect? I mean, why do we need to go optical? What, for the larger public, maybe this is a natural question to start with.
Yes, so in most homes and in older technology, you use electrical cables, and you still use electrical cables in the data centers as well, but it's a matter of application. And the reason for going to optical is because electrical cables, they depend on electrons to carry the signal, and that transmission generates heat. It's very, very, very lossy compared to optical transmission. Optical fibers rely on total internal reflection, and it could be considered lossless if it's ideal circumstances because of this. So mainly the loss, I would say, and the temperature generation in electrical cables. But then also there's so many benefits. You cannot tap an optical cable without this intercepting the signal. So it's much more secure in that sense. It's more lightweight. I'm not sure about cost, but silica is becoming much more easy to manufacture in large quantities. So yes, so complexity might be increased, but there are so many benefits with optical.
Right. So how long do you think one can go today at 25 gigabit per second electrical?
Well, we can go very long. It depends on what wavelength you choose. In data centers, we are limited by the latency. We don't want things to take too long, so we need to use a very high-speed technology. You said at 25 gigabit per second. I'm not sure the speeds they use in transatlantic cables, but in those systems they use wavelengths that have either the 1310 or the 1550. The 1310 is zero dispersion wavelength, and that 1550 is the very low attenuation.
Right. So optical, we know we can go 1,000 kilometers plus at the right wavelength with the right modulation format, right?
Yes.
So, but what about an electrical link at that speed? How do you think one can go electrical?
Oh, electrical. Okay, sorry. I guess it's would be an exponential decay of the signal. That's my guess, at least, that at 25 gigabits per second. I actually have no idea about the standards of electrical cables at that speed.
Yes, so what we have seen, just to put things in context for the optical interconnect, it's about a meter.
1 meter. Wow. I guess like 5 or 10, but 1 meter. Yeah.
Right. So already at that point we understand that even at today's data rate, we can't get too far on an electrical cable. And then you touch a little bit earlier on these items, of course, is the weight, size. These cables that are for the electrical interconnect already at 10 gigabit per second, they were extremely heavy, taking a lot of space.
Yes.
One of the key reasons going optical even before 25 gigabit per second was, for instance, the structural integrity of the data center building. They had to start go optical because of the weight the copper lanes will add to the concrete structure. It's kind of amazing and I would say unexpected in a way for us in the opto business. Anyway, so let's move to the next question. What do you think makes the VCSEL particularly interesting for this very short reach? You know, if you would try to explain it to someone who is not directly in our field, you know, it's
what makes the
why is a VCSEL such an appealing solution for the optical links?
Well, it is possible to make it very small. The circular, I mean, that's interesting. But for me, it's the small modal volume of VCSELs that make sure, because in optical interconnect short reach communication, we don't require very high power. You can distinguish between power levels that are much smaller than for some other applications. So you don't need a lot of output power or from the laser source or the light source. So VCSELs have the benefit of being able to have a very low threshold current, and you can operate them at very low currents in general. So the power efficiency is a big motivation between using VCSELs, and since the modal volume the structure makes them, you can manufacture them with a very small footprint, which is interesting for especially future generations of optical interconnect, because I believe that we will have much more integration and much more compact solutions that will actually require. Right now the VCSEL is in a huge, it's very small, but it's still a huge transceiver package, but I don't think that will be the case. So I think the footprint, the small footprints, is actually gonna be more important.
Right, and that of course in combination with its surface emitting characteristics, so
Yes.
we can make arrays out of them.
Yes, you can do on-wafer testing. Cost is a huge driving factor in data centers and short reach communication.
Good. So what do you think would be some of the key characteristics that are important for an optical link? You know, I'm thinking bandwidth, it's an obvious one, and we came several times to power consumption, but there are other things now.
Yes.
That will come to your mind first. You've been
the absolute first thing,
and trying to close the link in the lab, and you probably observe different key characteristics that you think are important for an optical link. Can you comment on this?
Yes, so you mentioned the bandwidth, so we want it to be high. But the second thing that comes to mind is linear conversion of the VCSELs. So you want the response to be as flat as possible. You don't want a lot of overshoot or very long oscillations that will give you, if the oscillations, the relaxation oscillations that occur as the VCSEL moves from one level to another are too long, it will interfere with the next bit if they don't level out before the next bit starts. So that will give you timing jitter unless the dynamics of the VCSEL are optimum or optimized in some way. And then let's see, so we have the bandwidth and the linearity of the response. And then let's see. I had a few more, but they totally disappeared.
Well, take your time.
Let's see. Could you repeat the question once more so I just get in the same
Yeah,
boat?
I was thinking if besides bandwidth and power consumption, is there
the power
any other thing, any other key parameter that you and of course jitter and inter-symbol interference that's related to jitter.
Yes, I was thinking about the temperature stability of the VCSEL and the reliability. So from a system point of view, VCSELs break. So I want a reliable
optical modulation amplitude. How important do you think it is in the or you were touching a little bit on this, on saying that on a short link you don't need that much power. That's true. At some point, I guess the receiver needs some minimum amplitude to close the link.
Yes.
Please comment on
so
this.
you need to consider your power budget. It's especially for higher level modulation. You need to have enough power in order to be able to distinguish between 4 levels if you have PAM4. And usually you can see in the bit error rate, the sensitivity measurements that we make, that we have received optical power or potentially OMA on the x-axis. So the sensitivity of the detector, you need to have enough power in order for the detector to be able to pick up the signal, and in order to also distinguish between the levels when you decode. So that's, of course, is a big and the fiber attenuates with 1 dB per kilometer at 1060. So that's 2 dB of loss if you go 2 kilometers.
Okay. So now you focused on single mode VCSELs, and why going single mode? Is that necessary, or is this something that we like to have? It's a nice to have, or is it a must, or at what distance would become a necessity rather than good to have?
So if you're looking at 1060, because we already know where the limitation is at 850. But if we look at 1060, I think it's a must-have still if you want to, because of the modal dispersion. If you want to, we haven't made a lot of tests with the multimode VCSEL and the multimode fiber, but I think it's still at a few hundred meters, less than half a kilometer, that you need to consider a single mode VCSEL. With the single mode VCSEL, we could, sorry for my bold language, but we could easily do 25 gigabit per second over 1 kilometer. It was a preliminary measurement and it worked just fine. So just switching from the multi-mode VCSEL to the single mode there was a huge step. And that's because of the mode competition and the modal dispersion. And now there are so many options coming up with fibers. They are looking into universal fiber, which is a few mode fiber, I guess, that has not, the multi-mode fiber has a 50 micron core, but this one has a 30 micron core. And I think they have a special alpha profile, like refractive index profile of the core. But they claim that the nice to have with the multi-mode options is the relaxed alignment, which is cost efficient in transceivers. But they claim that with the universal fibers that don't have the very narrow core as the single mode, which is 9 or 7 micrometer core, they still can have that relaxed alignment tolerance with the universal fiber. And then they have, in those reports I've seen, they use a few mode fiber, not the single mode one at all times. There's been a few tests with single mode VCSELs as well, but they use few mode VCSELs and seem to get pretty good results. So I don't think it's as black as white as going from a multi-mode to a single mode. I think you can maybe have some options with a few mode VCSEL, perhaps with the right fiber up to 1 kilometer, I'm not sure. But then I think that single mode VCSELs are essential above 1 kilometer, absolutely. But I'm not so sure about the fiber option actually. Selective modal launch is powerful in order to achieve long distance over multi-mode fiber.
Right. So already at 850, there are some fibers today that we try to use the difference between propagation between different modes to compensate some of the chromatic, right?
Yeah.
Sure. So how have you worked with true single mode fiber at this wavelength, or is
not standard single mode, but we had Corning make us a optimized single mode. It was, the cutoff was changed to accommodate single mode transmission at 1060. So the cutoff was around just under 1 micron. But Corning, the design was based on a standard model of a single mode fiber, only that they tweaked the cutoff frequency and reduced the cutoff frequency.
Okay. So how large is the core for such a fiber?
It was 9 micron, and then the mode field is a distribution, MFD, was 7.7, I think.
Yes. Hey, that's very exciting. We'll see now. Hopefully, development continues on the single mode VCSEL or around 1 micron wavelength, and that will, as you also mentioned, will drive the fiber development. So I hope there will be what should I say, an enhanced interest for the optimized fibers for 1 micron.
Yes.
Right. So let's dive a little bit into the VCSEL design and VCSEL technology itself. Now we are discussing essentially gallium arsenide based oxide confined VCSELs, but are there any other technologies that one may consider in this space?
Oh yes.
Anything else but oxide confined or arsenide based?
I'm glad you asked. Actually, the first VCSELs at around 1060 above 1 micron in this area that I'm working in, were made by NEC that used ion implantation in order to confine the carriers instead of oxides. Of course, you can choose not to do anything. You don't have to have an oxide. You don't have to use any more confinement than actually having the MESA, but then you would be susceptible to a lot of scattering loss and so on. So oxides reduce those problems significantly. Then you can choose to do ion implantation, which is it requires, if I'm not mistaken, a regrowth. So you etch a MESA to confine the carriers, and then I think you regrow with, or you implant. I'm not sure how that procedure is done, but it requires some fabrication that is complex in some way, as far as I understand it. I've never done ion implantation myself. And then you can also use a buried tunnel junction in order to get the lacing confined. And that it also requires some more complex fabrication, because you introduce you make a PN junction in the center of the device, and then you have to build a structure on top or around that. So it requires more complex fabrication. Oxidation is relatively simple to do, where you just expose your structure. We have aluminium in some of the layers, in a high aluminium content in some of the layers in our structure, and when exposed to water vapor at a certain temperature, they simply oxidize, and this introduces a little bit of strain, and it needs to be controlled, but it's relatively it's simple compared to the other methods.
Right. So what about the other material systems?
Yes, we have. You can make indium phosphide VCSELs. So with the indium phosphide, so the benefit of gallium arsenide is the manufacturability of the mirrors, mostly, because the mirrors can be made up out of lattice match materials, aluminium, gallium, and arsenide. If you look at the lattice constants of those, you can obtain a lattice matched DBR with reduced strain. And also, well, you can also do the same for indium phosphide if you have the right amount of indium. I guess you use InGaAs and then indium phosphide, and vary InGaAs and indium phosphide. So if you have a right amount of indium content in your InGaAs, then you can lattice match it with indium phosphide. But then the refractive index step between those material isn't as large. So that will require many more mirror pairs. So the mirrors will become large, or they will have many layers, which can be a downside. And you also have, let's see, you also have the free absorption, free carrier absorption is dependent on wavelength. So with the indium phosphide technology, you will have more problems with free carrier absorption, which is will give you more optical loss. It is the same with the difference
so
between.
you're trying actually with the gallium arsenide at 1 micron, you are trying to get the best out of both worlds. Right?
Yes, exactly.
What do you see as the key limitations of the gallium arsenide multi-mode pixel? Sure. We have in mind, of course, the single mode versus multi-mode difference. But is there anything else that you see is a key limitation that will force us to go looking into some other technology or some other type of design, except for the single mode versus multi-mode?
So you were asking about what is limited.
Yeah, I have in mind things like what's the intrinsic limitation on
the multimode
or noise or power consumption. So other things than the propagation itself, which of course might be.
And you're thinking multimode versus single mode?
No, I'm thinking more like this gallium arsenide traditional technology from the multimode pixel. The oxide confined essentially all-gas based pixels, maybe with a little bit of indium in the